Okay, so basically what I'm going to show you is a formula that you can use almost in absolutely any situation when it comes to mechanics. It is not for the conservation of momentum, so you won't use it for conservation of momentum. Okay, conservation of momentum, then you will use that the sum of the momentums is before is equal to the sum of the momentums after. That's what you will use for when you have two objects colliding and you want to know what is the velocity before or after. If you've given some other information, you will also not use it in an elastic collision. Okay, because in an elastic collision, okay, you are using this formula that the sum of the kinetic energies before is equal to the sum of the kinetic energies after. Okay, it's exactly the same idea as we have conservation of momentum. For momentum, we just use mass times velocity, and for kinetic energy, we use half mass times velocity squared. Okay, so that you'll use it there. You will also, actually you might be able to use it in conservation of mechanical energy. Okay, conservation of mechanical energy, which is that the potential energy before plus the kinetic energy before is equal to the potential energy after plus the kinetic energy after. Now if you say before and after, you can use initial and final as well. Okay, the formula that I want to show you, however, is actually comes from the work energy theorem. The work energy theorem. Okay, now we know that the work energy theorem, it tells us that my net work done, the net work done is equal to the change in kinetic energy. Okay, now change in kinetic energy is not kinetic energy, it's the change in kinetic energy, which means it's the kinetic energy half mass times velocity, okay, after or final minus the kinetic energy initial. Okay, so that's the formula. Now the formula that I want to show you though has got to do with what is net work done. Okay. Net work done is the sum of all the work that was done on an object. Now what can do work? What would you say? What can do work on an object?
Gravity.
Gravity. Okay, so we've got work done by gravity. Okay. We can have work that's being applied, so it's actually something that's physically. So I've got, let's say, a box on an incline here. Got an object on an incline, and there's literally a rope attached to it, pulling it up. Okay, this rope in the rope would be tension, or you can just call it the force that's applied. There's a force applied, so there's work that's applied. Okay, in this case, there's gravity working in on the object. Okay, another thing that can do work is there's another force here called the normal force. Okay, I'll look at this one just now. In the future we will actually not have this one at all, but I'll show you now why. Okay, and then there can also be friction. Okay, now friction will only be involved when an object is actually in motion. Okay, but then again, work will only be done when an object is in motion. If an object doesn't move, work won't be done, and I'll show you now in just a moment. But we can also do work can be done by friction. Now what is work? What am I actually talking about? Okay, so work is the product of force and displacement. Okay, now displacement, you can see if I'm not moving, displacement is 0. So an object that's not moving is no work is being done on it, or the work that's being done on it cancel one another out. Okay, so for example, a force is pulling it up, but because of gravity pulling it down, okay, they maybe cancel one another out, so it's not working. The other thing is the work is only done by the component of the force that's in the direction of the motion. So for example, if I have an object going from this point to that point, okay, so here's an object that's going to move this distance. This is the displacement, okay, but as I'm pulling it along this, I'm actually pulling it at an angle. Okay, so my force is at an angle, theta. So the part of the force that is in the direction of motion, or actually the direction of displacement, forms the adjacent side of a right angle triangle. Do you see that? This is the adjacent side. So if I want to know, I know that this is the force that's acting on the object. If I want to find what is the size of the component that is in this direction, how will I calculate that? You know?
Cos.
With cos, excellent. So in other words, the force that is in the direction of displacement, I'm going to write it like that, is equal to the main force times cos of theta. Okay, so in this formula we'll add another cos of theta, where theta is the angle between the force and displacement. Okay, now that is why the normal force will never do any work. And the reason why is that the normal force will always be at 90 degrees to the direction of motion or the displacement. So for example, the work done by the normal force is equal to the normal force times the displacement times cos, and now the angle between the force and displacement is 90 degrees. And when you do cos of 90 degrees, hopefully you know, but if you don't and you do it on your calculator, you'll see it's in 0. So the work done by any force that is perpendicular will always be 0 joules. Now work is energy. Okay. So how are we going to use this formula in absolutely any scenario that does not involve necessarily the conservation rules? Okay, let me show you the tremendous formula that this one provides. Just so you know as well, there could, for example, be another rope pulling in this direction. Okay, that's not impossible. We could have someone pulling it up and something pulling it down, and so pulling it down and friction will be in the same direction. So we could have more terms in this expression if we have more forces acting on it. Okay, so let me just quickly show you how this formula expands into a very big formula that has all of the variables that we might need. Okay, so I said that the net work done is equal to the work that is applied plus the work done by gravity plus the work done by friction plus work done by anything else. Okay, any other force. So any force acting on it. You see I took out the normal force. Now for this I'm just going to use an example of a box that's on an incline. So here I have a box on the incline. Obviously there's now different options that we could have here. We could, for example, have a force that is pulling it up. I could have no forces acting on it, so work applied is nothing, but I'm going to assume there's a force applied up. But actually before I do that, usually what they would ask you is to draw a force diagram or a free body diagram. Now first, what's the difference? A force diagram is just a dot with all the forces, so this represents the box, while a free body diagram would actually be a little sketch with all the forces. Okay, so body, think of body, then it's actually a picture. Force diagram, then it's just a dot showing all the pictures. So what I will do if I want to use this formula is I'll always start with a force diagram. Okay, so I'll make my dot, and on this dot what I'm going to do is show all the forces acting on it. Now do it in this order, it's just the simplest way to do it. Okay, obviously or you don't have to assume that it's not moving, but we're going to assume it is moving. Okay, and then I'm going to say I'm always going to start with a force that goes directly straight down. Okay, and this will be the weight. There will always be weight involved. Okay, so I know there's a force going straight down. After that, take a different color. Okay, preferably pencil if you're doing it in an exam, and show the direction of motion. Okay, the direction of displacement. In other words, where did it start and where is it going to stop? So we're going to assume it's going from here to there, for example. So I'm just going to show the direction of motion very lightly, more or less there, that's the direction of motion. This is the most important part of the sketch. Once you have the direction of motion, you can immediately put in the normal force, because the normal force will always be perpendicular. So I can now draw the normal force. Okay, so I make that 90 degrees here. That's my normal force. Okay, and I can also, using the direction of motion or the displacement, okay, I can now go and draw in the opposite direction the friction. Friction will always be in the opposite direction. So I've got my normal and I've got my friction. Okay, and now the question in this specific case, there's no way it can move up this incline if there wasn't a force that's being applied to it. Does that make sense? So there's definitely another force that's applied here. Okay, so we have this force going in this direction, which is the force applied. Now the reason why I said that this direction of motion or the direction of displacement is so important, because now what you have to do is you have to find the angle that each of these forces make with that. Okay, so, and the only one that's really difficult is we're going to say this is theta. Okay, the only one that's really difficult is actually the weight, the angle that the weight makes. We know that the angle that the normal force makes is 90 degrees. And we know that the angle that friction makes will always be 180 degrees. So the normal one we're just going to ignore anyway. I just drew the whole one. But the angle that friction makes is always 180 degrees. It's the angle that weight makes that I want to know. So what I do know is that this angle here is theta. Can you find a way to tell me what would be this angle? I know that this is 90 degrees. I want to know what is this angle, the angle between the displacement and the weight. It's an excellent opportunity to apply your geometry.
Yeah. So, what I was thinking, I don't know if you could do it, but if you could use, since the line for what do you call this? FG parallel.
FG parallel?
Yeah.
I'm not exactly sure what you mean.
I don't know how to explain.
Okay, well, for the sake of time, I'll show you that this is an external angle to a triangle. You see this triangle? There, one side is extended. What do we know is the theorem for the external angle of a triangle?
The two internal angles are equal to the external angle.
Cool, and we know this one is theta. So when I say theta, we know what this angle, they're going to give this angle in our question. Okay, so this angle plus that angle must equal this angle. So this angle is 90 degrees plus theta. Okay, now the reason why I needed this is because for each and every one of these, I have to now, I don't have any other force here, so I'm going to just ignore this one for now. Okay, but for each and every other one of these work, I'm going to substitute the formula. So work applied is force applied times delta x, the displacement, times cos of the angle between them. Now you can see that the force is applied in the same direction, so the angle is 0. Now gravity. Gravity is, what force is involved with gravity? What do we call the force of gravity? Weight. Good. So it's weight. So instead of weight, I'm just going to do this mass times gravity, okay, times displacement. You can see it's displacement, delta x, times cos, and in this cos is now that angle, 90 degrees plus theta. Okay, and then finally we've got friction, which is the force of friction, times delta x times cos of 180 degrees. Okay, so literally all you had to remember so far is this formula, that the net work done is just the work done by every single force acting on it, except normal force, because it's going to be the 0 anyway. Okay, the next thing you just had to remember is the normal formula for work, which is just force times delta x times cos of the angle in between them. And with that, you get this incredible expression. And look just at all of the variables in this expression. Okay? And we didn't even do the left-hand side. Now look on the left-hand side what we have there. The net work done is the net force times delta x times cos of the angle. But the cos of the angle, the net force, is always what causes the object to move. So the angle between the net force and the displacement will always be 0. So I don't even need this. Okay, I don't even need, because that's going to be cos of 0, and cos of 0 is 1. So on the left hand side, I simply have the net force times the displacement is equal to, and then I've got this expression. In this specific case, the applied force is also 0, okay, but it could be not 0, okay, between the applied force and the displacement. Okay, so just in this formula, notice that you can almost go and calculate anything when it comes to forces. When forces are involved, you've got all of your forces included here. All you need is all of the values except for one value. Then you can use this formula. However, okay, and I just want to show you this as well. Okay, in trig, we learned how to simplify this expression. Cos of 90 plus theta. What does that simplify to?
Sine.
Not exactly.
Negative sine.
Negative sine. I don't know why it's doing this. Okay, so this would be negative sine. So I just want to show you this. Mass times gravity, delta x, negative sine of theta. Okay, so forget about exactly what this is, but you will notice that delta x sine of theta, if this is delta x, sine of theta actually calculates this height right there. Okay, which means that this formula could even change to be mass times gravity times height. Delta x times sine theta, that's what this is, the height. It's the difference between here and there. This height is delta x sine theta. Okay, what is mass times gravity times height?
Potential.
That's potential energy. Now, this is therefore, this work done by gravity is the change in potential energy. Okay, the work done by gravity is, but notice with a negative in front. So the work done by gravity is equal to negative the change in potential energy. Okay, on this side, when it comes to friction, the cos of 180 becomes negative 1. And friction will always be in the opposite direction, so it will always be cos of 180, so it will always just be negative F times X. Okay, so force applied, let's now assume that it's just cos 0, so that it would just be 1. Just want to show you this. So you can see here, again, a very lovely formula, and I want to show you here that these two terms become negative. And the reason why they become negative is because work is energy. Work is the ability to do energy. And when I push something up an incline, okay, friction steals energy. And because I'm going up, gravity steals energy. If I was pushing down, then this formula would have been 90 minus theta. I'll show you that in a minute. 90 minus theta. And cos 90 minus theta still is positive. So if I'm pushing it down, then gravity would be adding energy. Friction will always be negative here, so friction will always steal energy. Force applied it will never be in the opposite direction as the motion. Well, it could, and if it is in the opposite direction of motion, then it's stealing energy, okay? Because it's taking away from the thing moving, because it's pulling in the opposite direction, so it's stealing energy from the object that's moving. Now, you'll see here, the net work done, we said, is equal to the change in kinetic energy. Okay, so what we mean by that is if this adds energy to the system because it's positive, this subtracts energy from the system, and this subtracts energy from the system, okay, if I have more energy that was added, okay, I will have a surplus, a profit almost of energy. So what will happen with the extra energy? It will go into motion. It will change the kinetic energy. It will cause the thing to move. Okay, faster or slower. That's what will happen with the profit energy. If, however, I am stealing more energy than I'm adding, then I will have a loss. Then, in other words, this side will be negative. The whole side will be negative because I've got more negatives. So what will happen now is that my change in kinetic energy will be negative. That means my future velocity will be less than my initial velocity. I'm slowing the thing down. Why? Because the parts that's stealing energy doesn't get enough from this one, so it needs to take some from the motion. Okay, it's a little bit theoretical at this point. When I do some examples, you'll really see. I just want to show you now the whole formula. So you have an option. Sorry, let me continue here first. The net force can also be written. Remember, there's a theorem that says that the net force is equal, or actually that acceleration is equal to the net force divided by the mass. Okay, or that the net force is equal to mass times acceleration. So I can change this formula even more effectively, because I might not know what the net force is, but I might know that I have a mass and I have certain acceleration. Okay, now look at all of the variables in here. I've got acceleration I can calculate mass, I can calculate displacement, the applied force, gravity, well, that's a constant. I can go and calculate the angle that is made. If I'm given all the other forces, I can calculate friction. There's so many, as long as I'm given all the formulas. The other thing, though, is this change in kinetic energy. Okay, so I can have the same formula, but instead of using net work done, I can use change in kinetic energy. So I have, instead of net work, which is what this is, I can have the change in kinetic energy. But the change in kinetic energy is a half mass times velocity, future velocity squared minus initial velocity squared. Okay, is equal to all of this. I'm not going to write all of that. That's a lot of things. But I just want to show you can also use this formula, and all of a sudden you've got velocities in here. Okay, so you can use this whole formula to calculate certain velocities. You can use this when we do forces. This formula can be used with forces, with projectiles, and with most energy scenarios. This is question 1, question 2, and question 4 in your exam. You can use a single formula and it will always work. Okay, so let me do some examples and then you'll see I'm not lying.